Okay, so basically we just we use the fact that this is equal to 0, and we take the derivative of sine naught. Okay, and okay, so we've basically just rewritten this h bar d by dx plus m omega x times sine operating on sine naught is equal to 0. Okay, and then we can rewrite this again as d sine naught over sine naught is equal to minus m omega x dx over h bar. Okay, and so now we have something that we can integrate. If you remember, if you integrate a function divided by that, integrate the derivative of a function, the differential of a function divided by that function, we basically get the natural logarithm of the function. And here, if we integrate minus m omega over h bar times x dx, we just get x squared plus a constant. So we get x squared over 2 plus a constant. And so after we do this, we have ln of sine naught, okay, is equal to minus m omega over 2 h bar times x squared plus some constant. Okay, and if we now take the raise both sides to if we take the exponent of both sides, so if we go e to the ln e to this whole thing, then we get e to the natural logarithm is just the function, the argument right back, so we get sine 0 is equal to e to the minus m omega x squared over 2 h bar. Okay, and now this e to the c just basically that multiplies this just becomes another constant a. Okay, so all the constants go into this amplitude function on the exponent here. And so what we see actually is that the ground state wave function, okay, is equal to some normalization constant times a Gaussian function. Remember, a Gaussian function is where you have the e to the minus some constant times a spatial dimension squared, or some parameter squared, in this case x squared. Okay, and so the ground state wave function is going to look like a Gaussian. Okay, so then in the ground state wave function squared will also look like a Gaussian. The square of a Gaussian is a Gaussian. Okay, and so we can find the normalization constant e by normalizing, that is by requiring that that the integral of the wave function over all space is equal to 1, because we basically have to find the particle that's represented by this wave function somewhere in space. Okay, and so if we set equal to 1 the integral from negative infinity to infinity of psi 0 star, and remember this is a function of x, times psi of x dx, what we get is the absolute magnitude a squared. A in general can be a complex number, and so we need to take the complex magnitude, the absolute magnitude squared, times the integral of e to the minus m omega x squared over h bar. The 2 goes away because we've squared. Okay, and this is dx, which is equal to, if you look up this integral, what you'll find is the value is equal to, when you're going from minus infinity to infinity, is equal to pi h bar over m omega. Okay, and so we're left, and this is equal to 1.